Everyone, today I will be talking to you about Bayesian optimization. I'm going to be describing simple techniques, so to say, and going to advanced techniques like meta-Bayesian optimization. So if you know the basics of Bayesian optimization and you just are interested in learning about the meta-BO, please skip the first part of the session and go to the last part of the talk. This is a talk that I gave during the fall school of AutoML, I believe, that was held last year. So I'm hoping it would be useful for everybody to have a look at. So to start, let's frame the problem we're interested in. So the problem we are going to be focusing on is a problem that looks like this. So we want to try to maximize some function f of x with respect to certain constraints on that variable x. So I'm looking for that variable x such that I can maximize my function f of x. Now, this problem, right, has been widely studied in literature, and there are so many constraint optimization algorithms. So why should we even bother? Why are we even interested in this problem? Well, we have two properties that will make this problem extremely interesting and not easily accessible by current solutions. The first property is that this function f is a black box function. So I don't know, right, the equation of this function. I don't know the closed form equation for this function. It's unknown, right? I'll give you an example or a set of examples why this is the case. So because I don't know, right, this black box function, then all I can do is I can talk to this function, query it, give it a variable x, and then ask it what's the value of f of x you think corresponds to that variable x. But to make matters worse, we also know that this function is very expensive to query. It will need hours or days to return one evaluation for a variable x that I'm trying. So I have a problem where my function is a black box and it is expensive to evaluate. So I can't really go around, the standard machine learning way where I just collect tons of data about this function because this function is very, very expensive to evaluate. And that also goes for the constraints. So the constraints are black box and they are also expensive to evaluate. Now, given those properties of my function, what are the properties of an optimizer I would be looking for to find that variable x? So what should my algorithm that tries to optimize for that variable x do? What should it look like? Well, there are a couple of things that come to mind, right? So first, we need a data-driven solution, right? Like this is basic, right? Because we don't know the value of the function, the equation of the function f of x. So what we're going to do is we need like a data-driven form of solution. That data-driven solution would be, okay, I'm going to query a variable x, I'm going to try something, I'm going to get feedback about the function value f of x, and I'm going to try to improve, right? So I'm going to take x and get f of x, right? And then I'm going to try to improve my guess so that I get closer and closer to the optimum x star. We also need a data efficient solver, right? So we need a solver that would not query so many times that black box function because it's expensive to query. So therefore, I need a data efficient solver that reduces the number of queries I make to my black box function. Since I don't know that function, right, I would also need a solver that can go beyond the gradients, right? So because my function itself might not be differentiable, I don't know it, right? So what I really need to have is a solver that can go beyond the gradients. And of course, I need to be feasible with respect to my constraints. I need to satisfy my constraints. Right, so now this is a setup. This is the setup we're interested in. We want to maximize a function f of x, which is unknown, i.e. black box, expensive to evaluate, subject to certain constraints. So, okay, what are sets of examples where this could occur? Why is this an interesting problem for us? Well, Maybe the most well-known setup of this problem is the one related to hyperparameter tuning, right, from machine learning. So any one of you who has worked with a machine learning set of models, you know that to train those models, you typically, so to train, i.e., to find the weights of these deep networks, for example, you need to provide a set of hyperparameters to your algorithm, to your training algorithm. So, for example, this could be the learning rate of Adam, right? The number of units in a layer, the number of layers, etc. These are set of hyperparameters that we need to provide a training algorithm before we can train for W star. Okay, good. So how do we typically do it today? I mean, although BO exists, many people, I believe, still do that manually, right? So, you know, we fiddle with the hyperparameters based on our experience, based on our priors. But in this talk, right, we're not gonna do that. What we're gonna do is we're gonna try to automate this process. I'm gonna design an algorithm, right, that will give me those hyperparameters. So to do that, the first change I'm gonna do is instead of having a human deciding on those hyperparameters, I'm gonna have an agent which will tell me what are the value of those hyperparameters. So that agent, right, as an output, it will give me, okay, I believe the value of the learning rate should be that, the value of the units in the second layer should be that, I need to have 10 layers, and so forth. Upon deciding this and given a training data set, the training algorithm would run. Now, as the training algorithm runs, like for example, minimizing a loss, like a cross-entropy loss, you will get the optimal weights, or really the stationary weights of your deep network, W star. So please notice the distinction, right? The hyperparameters are not the W stars. So the hyperparameters are not the weights of the neural network. Given the hyperparameters like learning rate, etc., the Adam algorithm or whichever optimizer will minimize the loss and give you this W star. So given that, what do we typically do next? Well, what we do next is we validate those W stars on a validation data set, right? So what we do is we take those W stars that we have trained, right? And in addition to a validation data set not seen during training, and then I validate my algorithm, my W stars, by computing the specific validation loss that I have. And typically, if you are like doing it manually, you would look at this validation loss, and then you would be like, okay, yeah, I'm overfitting. Maybe I should increase the parameter of my regularizer and so on. But rather than doing that, what we're going to do in today's talk is we're going to give the feedback to the agent such that the agent will decide, right, to give me the new set of hyperparameters that it thinks will maximize my performance. So notice what I've done. I've just changed the standard loop in which we do hyperparameter tuning manually by allowing an agent to make those decisions. And the agent should make those decisions based on a set of validation losses that it has tried before. Okay? Right. Now, what is the issue here? Well, let's look at what type of function we are trying to maximize or minimize, right, with respect to those hyperparameters. Because remember now, my goal is to find the hyperparameters. So my variable x is the hyperparameters. And what am I going to try to do? I'm going to try to minimize my validation loss. So the x and y that I can collect, or the x and f of x, x is the set of hyperparameters, right? So x is the set of the hyperparameters that I will try. And f of x, right, is like the validation loss, which is the feedback that I will give back to the agent. Now I'm going to store those, like those trials in some memory. And then what I'm going to do now is, based on these things I've tried before, I'm going to try to get a new set of hyperparameters, which is better and better and better. Now, as you notice here, hopefully you already see it, that the problem is that the training step is extremely expensive, especially if you have a lot of data or large model. And it is also very hard to differentiate through W star in order to update the set of hyperparameters. So in reality, this is also a form of a black box because the gradients are hard to come by. So why am I talking about gradients? Maybe I already confused you here. But notice that if I want to solve my problem in a gradient way, I need to compute the gradient with respect to my optimization variable, which is the hyperparameters. But here I cannot do that because this has to pass through a optimizer and then through a validator in order to give me the function I'm interested to deal with. So consequently, I have a problem, which is the hyperparameter tuning problem, big problem, very important problem in machine learning, which is really a special case of my function, of my black box optimization problem I wrote in the previous slide, where x is the hyperparameters and f of x in my example here is the validation loss. Okay, at this stage, many introductions for Bayesian optimization stop. And we of course, this is a very important problem, big problem, but at this stage, this introduction stops. I want to go a step further, and I want to tell you a bit more examples of this black box problem that we have been working on, which are critical and important to motivate further that Bayesian optimization solvers, right, are not just hyperparameter tuners. They are a broader set of optimization algorithms. So I will give you 3 examples. One is based on logic synthesis problems, which is a set of problems related to EDA, like chip design. I will also tell you about MIP, maximum integer programming problems. And I also will tell you about some very exciting work we've done on antibody design. We will talk about those, and then we will talk how we can formalize those as instances of my black box optimization problem. Right. So let's get started with logic synthesis problem. Okay. What I show you on the left side of this slide, I show you the pipeline of designing chips, right? So the design of going from specifying what you want in the system to, the chip itself. And it has really many processes. One is architectural design, where we, design, okay, what we think the architecture of this chip should look like. Then we have a RTL design, then we have logic synthesis, then we have the physical design of the chip, then we have the verification, the fabrication, and then finally we go to the chip. For sake of this talk, it's not really important to understand each and every block in this figure. What we are interested in is a problem in between, which we call logic synthesis, that what it does is it transforms, your RTL language, like your language describing what the chip should do, into a physical design. So it will map that, into gates like AND gates, OR gates, and so on. Now, how does this step work? And as you see, this is an important step. If this step is optimized badly, you might end up chips with large delays or big chips. So this is a critical step. And how does it really work? Well, the first thing is that you would take a Boolean function you would like to model, right? And then you will take that circuit, and then you will transform that circuit into what we call AIGs, and inverter graphs. So those AND inverter graphs are an equivalent representation of your circuit, but using a graph which only have a set of nodes that are AND gates or inverter gates. And they are connected together, right? By the circuit itself. Like how the circuit looks, you will have an equivalent AND inverter graph representation of it. Now, in addition to these AIGs, we are also provided with a bag of C++ operators. So this bag of C++ operators, it has a varying set of operators that can execute on top of this graph. So for example, it could decide to resubstitute a node in the graph, it could decide to refactor a node in the graph, and so on. And each of those operators come with its own set of hyperparameters. So we have this AIG graph, and then additional to this AIG graph, we also have this bag of operators where I can take an operator, execute something on that graph. Each operator is a C++ code, and they have a set of hyperparameters on top. Like you provide these parameters to dictate what this operator is supposed to do. So here I give you an example from like an open source example of one of those operators from a library called ABC. And this is, for example, an NTK refactor operator. So this is an operator which will refactor nodes on the graph. This operator takes some inputs which are like pointers, to where you want to execute these things. But also it takes this set of parameters, right? Like the node size max, the cone size max, the update level, the F0s, the verbose, whatever. And those hyperparameters, they could be mixed. So for example, what you see here, they could be varying from Boolean to integers, and could also be continuous values. And then it will execute certain things depending on the choice of this theta n. Now, please notice, right, that we are not interested in all the details, right, of what's happening in this operator, but I just show you an example of one of those operators, like this an theta n, right, where an, is dictating what you should do, right, and theta n is telling you how you would do it by setting up those values of the hyperparameters. Okay. Now, what is our goal? So we have this AIG, and we have this set of this bag of algorithms. What is our goal, really? So our goal is to find a sequence of those operators. So, which operator goes where and in what order, and their corresponding hyperparameters. So I want to find the optimal sequence, right? The optimal order of those operators and the corresponding hyperparameters for each of the operators, such that I maximize what we call a QOR, or quality of results. So the idea is that I would like to find that optimal sequence, what I call sequence star, right? That will maximize my quality of results, which is a performance measure. So this performance measure depends on the order by which you put these operators, and also on the parameters you provide for each of the operators. Now, what does this performance measure actually measure? So this performance measure, what it does is that it measures two critical properties of your resulting physical design, right? So it will measure the area, by which you would like to have your circuit. And it'll also measure the delay of how much time, a signal would need to propagate through that circuit. And of course, now our goal is to pick the right sequence of operators and their corresponding hyperparameters, such that, we achieve very small area because we have billion-sized circuits, right? And also don't have a high delay in signal propagation. And of course, we have a set of constraints as well on the allowable ranges and the sequences that we can execute. Right. Now, notice that this problem, right, is a problem in logic synthesis, so it has nothing to do with hyperparameter tuning per se. And also, it has the following two properties. One, the computation of the QOR is very, very slow, especially when you have very big circuits. So to compute the QOR for one sequence is going to be extremely slow. So i.e., it's going to be very expensive to query so many different sequences and their corresponding hyperparameters. Two, to compute this QOR, we have a nesting of C++ algorithms. Let us explain this, right? So imagine you have your original AIG, then you pick, right, a operator to execute. You change this graph, right? So this operator is a C++ code. It will execute on this graph. You will change the graph. And then you will apply another sequence or another operator. Then you change the graph again, and so forth up to, like whatever the length of your sequence is. So as you see, it's extremely hard to write a closed form equation of the QOR as a function of the sequence, because each of those is a C++ algorithm which has its own hyperparameters. It changes the graph in some way and then creates a new graph that goes into another operator and so forth. And that's why we have a nesting of these C++ algorithms, making it extremely difficult to write a closed form equation of this problem. The other problem is that the QOR function itself is not differentiable, because the sequence is a discrete entity, right? It's like, you pick this, so you cannot differentiate through it. And the constraints, they are also not so simple, because they are involving complex algorithmic checks. So now we see that this problem of logic synthesis, of optimizing those operators and their hyperparameters, is actually a problem, right, that is a black box. So we don't know the closed form equation of that, right, because of the nesting of the algorithms, and it's very slow to compute. So it's expensive to compute that thing. So now we see that this is another instance of my general problem that I started with in the first slide: maximize f of x subject to a certain set of constraints. Okay. So hopefully I convinced you at least there is one application beyond hyperparameter tuning. Now let's go into MIP tuning problem, which is another application. So a maximum integer program is a problem that would look like this, right? So you would like to maximize, a linear cost or linear function, C transpose x, subject to ax is less than b, so like some inequality constraints and positivity constraints. But what makes life harder is that these variables x are actually integers, right? So we need the x's to be integers. They cannot be like real numbers, making this problem very complex to solve. Now, this is not a made-up problem. In fact, these MIP set of problems are widely used in industry everywhere. Applications go from production planning, scheduling, telecommunication, cellular networks, even to energy flow optimization. So in reality, this problem, if you are able to crack it, right, then you can solve so many problems. And to many of you, I don't really need to motivate why maximum integer programs are important, or problems are important. Now, given its importance, right, there has been so many heuristics developed, right, to solve this type of problem. How you would branch through these variables x to solve the MIP, etc. So there are many, many, many solvers for MIPs. We are happy with those solvers, right? But we are not happy with the parameters that are used for those solvers. So let me give you an example of what I actually mean by this. So there's a very open source, right, like solver called SCIP. So this is an open source solver where you can actually provide for it an MIP task by giving it the matrix A, the vector B, and the vector C. So the vector B and A are for the constraints, like the inequality constraints, and C is for the cost, right? And then you would also give it a set of hyperparameters. They are about 200 parameters between mixed, discrete, continuous, and Boolean. And then given those two, it will give you an X star, which is kind of the optimal feasible solution of your MIP dictated by your input, right? So we have this SCIP solver. This SCIP solver will take an instance of your MIP, a set of hyperparameters, and then it'll give me, the value X star. The problem is that the set of those theta parameters, the hyperparameters for this SCIP solver, right, it affects a lot the time it takes for this SCIP solver to produce a solution for you. So one setting, right, it could make it very, very, very slow. One setting could make it very, very fast. One setting could make it kind of okay. Now, the problem is that setting those value theta is extremely difficult for a practitioner. Here's an example of this value theta. What you see is there are different types of these parameters theta. So for example, there are like a separating thingy, right, which is a real number. There's a Boolean thingy, which is a Boolean variable, like this other separation is a Boolean variable. There are variables in theta, which are integers. And there are variables which are even categorical. So now it takes a lot for human experts to actually set those hyperparameters right. And it's extremely interesting or important problem, because if you set those parameters correctly, then you might improve the performance of this SCIP solver. And now please notice that the solution I'm going to be talking about later on is not tied to SCIP. If you have any problem that is related to things like this, right, like to setting such hyperparameters in whichever field, BO will be very, very useful for you. Okay. So what is our problem really, right? So our problem is we would like to minimize the running time of this SCIP solver with respect to this set of hyperparameters theta, right? So we would like to minimize the running time with respect to this hyperparameter theta. And we have constraints on those parameters theta. So for example, as I showed you, some theta need to be Boolean, another set of theta need to be integer, a third set need to be something else. So this is really the formal problem that we're interested in. The issue, however, is again, to compute this running time for the SCIP solver, it actually can become very, very slow depending on how big your MIP is. So it could actually take weeks, right, to just evaluate one set of hyperparameters. And this is not an exaggerated number. If your problem is big enough, you will take even more than weeks to recover or get back a running time value. Now, the SCIP itself also involves a nesting of algorithms, because depending on this theta parameter, different heuristics get executed. So it's really very, very difficult, right, to write this running time SCIP in closed form because of this nesting and because of, it's very hard to model running time in general. And if you notice, it's also very difficult to compute the gradients of this, right? Because there are variables that are categorical or Boolean or integers that are hard to differentiate through. And here we would like, to actually meet these constraints, about these allowable ranges and so on. So yet again, in this set of important problems that will cover a broad spectrum, ranging from simple production planning to energy minimization problems, we have a setup which requires us to minimize a function with respect to theta, right, in this example. But this function is a black box because we cannot write it in a closed form. And it's expensive to evaluate because it can take days or weeks to evaluate a trial of theta. So as you see, we're back to the original problem. We have a problem where we need to minimize, in this case, a black box function. I cannot write it in a closed form, subject to certain set of constraints, and that function is very expensive to evaluate. Okay? So these are two problems that are going beyond, just standard machine learning hyperparameter tuning, that demonstrate that this setup, this BO setup, is broad enough. And now we will go into one more kind of work or problem that is also related to the to BO, which is antibody CDR3 design. Okay. Now, by no means I am a medical person. However, we collaborated with this work with many amazing medical people. that have the experience and taught us a lot about the antibodies. So take what I say next with a grain of salt, because I'm not the expert here, but I'll just try to formalize the problem for you from a mathematical perspective. And if there are any assumptions or things we made up that are not exactly accurate in the real world, please take that with a grain of salt. Okay, so what is an antibody? So an antibody is a type of protein that your immune system makes to attack invading pathogen, right? So if some pathogen enters your body, then your body will start trying to make those antibodies in order to attack and neutralize that pathogen. The antibody itself looks like a Y shape, like I show you here, and it has two chains. It has a light chain and it has a heavy chain. On those chains, there are variable regions and there are constant regions. We're not going to bother ourselves a lot with those. What we are mostly interested in this work is maybe a narrow version of the antibody, which is on the tip of the antibody, which we call the CDR region, or complementarity determining region. Now, this region is the region that allows the antibody to specify to a specific antigen. It has 6 variable loops. 3 of them are on the light chain, 3 of them are on the heavy chain. So we will be interested only in this small chunk, right, of the antibody for now, which allows us to kind of now play, right, with those different loops we see here in order to make the antibody more specific to a different type of pathogen. Now, what are those CDRs made of, right? The CDRs themselves, they are chemicals, right? And they are made of amino acids. They're like any other type of protein. They are made of these amino acids. And those amino acids, they contain an amino group, which is NH2, and a carboxyl group. So you will see in those amino acids, which are 20 to 22 from, you would see that there are they always kind of start with an amino group, which is like this NH2, and they end with a carboxyl group, which is what you see there. And then what happens, right, is that those come, in a sequence after each other, and then they will start combining together in order to form for you the protein. There are 20 to 22 amino acids, like alanine, cytosine, glycine, and so on. We're not really exactly bothered by the specificities of each one of them. We just want to know they are amino acids. Now, how do we make proteins? We make proteins from forming peptide bonds between these different amino acids. So we will take one amino acid, we will take another amino acid, and then what happens is that the amino group, the NH2 group, will act with the carboxyl group. They will form a peptide bond and they will emit water. And now this can happen often, across many times. And then that will form for us a polypeptide chain, which will form the protein. Typically, there are 500 to 4,000 amino acids in sequence. Right. And now please notice that the order by which these amino acids happen actually matters, because like I show you here an opioid modulating perception of pain sequence of amino acids, which is made of tyrosine, glycine, phenylalanine, and leucine. But now if I flip things over, then we don't know what this thing can do. It doesn't have any pain modulation effects. Right. So now what is your problem, right? Like, let's think about what we want this tip of the antibody to do, right? So as this pathogen or antigen, right, when I write antigen here, as this antigen enters your body, right, what we need to do is we need the antibody to design a CDR sequence, right, that has a good binding equality against the antigen, so we can actually neutralize that antigen. So the antigen enters my body, right? And then after the antigen enters my body, I want to design that sequence of amino acids that will have a low binding energy with respect to my antigen. So why low binding energy? Because things become more stable and nicer and so on. So imagine for now, there's some oracle or computer, which will give you the binding energy if you give it a sequence of amino acids and an antigen, right? And then your goal as an agent is to find that optimal sequence of amino acids that will minimize the binding energy with respect to your antigen. On top, right, you also have a set of constraints because not all sequences are good sequences. Some sequences might have high toxicity. Some sequences might not be stable enough. So what you really want to do is you want to find that optimal set of amino acid sequences that will bind well to your antigen while having a good constraints, right, or meet, the constraints. As I showed you, the order matters, right? So now you have a combinatorial problem. And that combinatorial problem will have a so big search space that will make it very, very, very hard, right, to be able to find the solution. So it's really like looking for a needle in a haystack, where kind of the haystack, is bigger than the universe itself. Now, the binding energy computation is not differentiable. As you see, it's a discrete entity anyways. And in the real world, to compute this binding energy is very, very expensive because there are two ways you could actually do this. You can either go through simulation, and that involves maybe complex physics-based simulations, so it's very slow to compute those. Or you can do the real-world experiment where you can just make somebody manufacture the antibody for you. And that is really expensive money-wise and time-wise as well. So now, yet again, we have a problem where we want to minimize the binding energy, right, which is a black box function, right, because it's very hard to write the equation of how binding happens, between an antigen and an antibody. It's also very, very expensive to evaluate. So yet again, we're back to the original problem, where we have a problem where X in this case is sequence and f of X is the binding energy. That is very hard to write in a closed form, right? And it's also very, very expensive to evaluate. So it's really expensive. So black box, expensive to evaluate. Right. So I hope that I have convinced you by now, right, that those three problems, that Bayesian optimization is actually important and actually applies beyond hyperparameter tuning and machine learning tasks. And what we're going to do in the next lecture is we're going to talk about how we're going to actually solve these types of problems. We're going to build a data-driven approach, which is based on Gaussian processes. And then we're going to discuss after that meta-Bayesian optimization next. So this is the first, I think, in a three-set lecture. And I hope you enjoyed this first one. If you have any questions, please leave them in the comments below. And I would be very glad to answer them. And then stay tuned for the next lecture, where I'm going to describe how you would solve those problems and talk about a library that does that. And then after that, we're going to jump to advanced techniques, talking about meta-Bayesian optimization. So with that, I thank you, and I will see you in the next lecture, where we talk about how to solve this problem.